Now let's try to learn how to create a new solution database. So in order to create a solution database, we have to go to this solution model here. So basically, we can make ideal solution or regular solution or in general solution by using this solution model. Okay, so let's click. And if you click the solution model, you can see that this the blank window in the beginning. And here you can find actually general information about the solution model by clicking the help menu. And then there's the general introduction about the solution. And also you can find the solution model and some examples. Okay. So let's click this one, solution model and examples. If you click this file, you can see this one. So let me briefly show you uh, the the general concept about the Gibbs energy for the binary solution first. Okay. So in FactSage we have the many solution model. So for example, the very first one is the one sublattice polynomial model, which we call it as model number one. And in this actual solution model, the most important one is it assumes the random mixing of the species in the solution. Okay. So for example, in the ideal solution, we assume that the species is mixing randomly. So that's the ideal mixing. So that is same as the random mixing concept. Okay. And then excess Gibbs energy, which is the non-ideal part of the Gibbs energy of the binary solution, it's coming from the interaction between the species. And those kinds of interaction can be expressed by the different polynomial forms. So we can use the very simple polynomial form, or we can use the, for example, Ledley-Kister type of the polynomials, or Legendre type of polynomials as well. So you can choose any of this one in the model number one. Okay. And also, when you go to the modern ternary system, then we can use the so-called interpolation technique to predict what's the Gibbs energy of the ternary solution from the binary model parameter. And in the FactSage, we are providing typically three different type of the interpolation technique. The very first one would be the Kohler type of interpolation technique, and then Troop and the Mujano type of the interpolation techniques. Regarding the interpolation technique, I'll explain that again when you go to the ternary solution. Okay. And also there's the different models, so model 7 and then model 12 or model 20, and especially this model 20 or model 12 and 20 is so-called compound energy formalism. We'll try to actually, in this actually the thermodynamic course, we are not going to actually learn this one. But if you are learning the FactSage course, we're going to see that this actually the compound energy formalism. And also we can and then let's go to the next one. And then one of the most important actually model FactSage provide is the so-called modified quasi-chemical model. And the classical modified quasi-chemical model is called model number 3. And then we modified this, we actually update this the classical modified quasi-chemical model, model number 3, with a little bit more the flexible actually form. That's we call it this one model 98 or model 99. Okay, so model number 3 and model number 3 is used to describe the quasi-chemical solution by using the so-called equivalent fraction as access parameter. But in the model number 8, we are using the bond fraction in the description of the excess Gibbs energy. So that's actually the one important difference. And also in the model 98 and model 99, we can choose the coordination number of the species in each binary system. So we don't have to use the fixed coordination number of the species within the multi-component system. So in each binary system, we can assign different kinds of coordination number for the given species. So that's also another big advantage of the model 98 against the model 93. Okay, model 98 again compared to the model 3. Okay, And also there's some other advantage in the model 98 and model 99, and I will explain this one later. And also we have the so-called ionic liquid solution model, and this is actually typically used by the smoke calc to describe the uh, oxide melt solution. And we actually also provide this model as a model 13. And then model 2 is so-called unified interaction parameter formalism. So this is similar to the Wagner interaction parameter formalism. In the Wagner interaction parameter formalism is typically used for to describe the dilute solution. So, for example, in steel making, you can actually describe the liquid ion-rich solution with some impurity element inside in the ion solution by using the so-called Wagner interaction parameter formalism. Okay, and however, Wagner interaction parameter formalism itself is not satisfying the so-called Gibbs-Duhem equation, Gibbs-Duhem relationship. So that's why Pelton and Bale introduced the modified actual version of the Wagner interaction parameter formalism. That's so-called unified interaction parameter formalism, which can satisfy the Gibbs-Duhem relationship. Okay, that's so-called model number 2. In FactSage, for example, FELQ database and also CULQ database, PBLQ database. So many liquid solution database in the FT miscellaneous database is actually described by the so-called unified interaction parameter formalism or Wagner interaction parameter formalism. Okay. And then also we have the model number 5, which is good for the picture solution. So this we call it picture model, and this is for the ion. So this is for the aqueous solution, which containing the different kinds of ion species in the H2O. So that is actually described by the so-called picture model. So let's look at the little bit more detail about each model. So we'll start with the model number 1. Okay. So this was the random mixing model. One sublattice random mixing model, or one sublattice polynomial model. Okay. So when you look at the Gibbs energy for the one sublattice model, is typically described in this way. So Gibbs energy of the binary solution, for example, is mole fraction of A, Gibbs energy of the A plus mole fraction of B, Gibbs energy of B, and then Gibbs energy of A, Gi, for example, was Gi naught plus RT ln activity of I, and then if you express that all together and then just reorganize them, then you can actually get this kind of the equation. So XA GA naught plus XB GB naught minus T delta S ideal of mixing plus XS parameter. And then this XS parameter can be described by the different polynomial actual function. When this XS parameter becomes 0, we call it ideal solution. When this XS parameter, GXS parameter, is the omega XA, XB, then we call it as a regular solution. And then if it is the more complex than that regular solution format, then we call it as a general solution. Okay. So, for example, if you look at the Gibbs energy of AG and the CU binary liquid solution, for example, here. So this is the AG Gibbs energy, pure AG liquid Gibbs energy, pure CU Gibbs energy, and this shape here, this Gibbs energy curve, can be made by this delta S of ideal entropy with temperature term, and then excess Gibbs energy term. So we can describe the excess Gibbs energy by using different polynomial functions. So one of the most simplest polynomial function is this one. So we can describe excess Gibbs energy as a QAB ij is just the index, and then XA power I, XB power j. Of course, in this case, I and j, both of them should be higher than 1. Okay, then we can have we can use this kind of interaction, this kind of polynomial to describe the interaction energy between the A and the B species. Okay, and this QAB, of course, can be function of temperature. Okay, and this is most simplest polynomial. But we can also use so-called Redlich-Hist type of the polynomial function. Redlich-Hist type of polynomial function. And this is the typically expressed by this way. So you have g access parameter is LAB. So this is the parameter, which is function of temperature. And then by default, we multiply XA, XB, okay, power 1, 1. And then we multiply XA minus XB power I. And this I could be higher than 0, okay? When I is 0, basically, then this I equal to 0, then this term will be 1. And then when LAB equal to constant term, then this is the same as the regular solution, okay? And then we can also use the so-called Legendre polynomial function like this, okay? And most of the time we don't use the Legendre polynomial, so we typically use this the simple polynomial function or Redlich-Hist type of the polynomial function, okay? And by the way, between this the Redlich-Hist type of polynomial and simple polynomial, we can actually convert 100% from one to the other one, okay? So basically, it's just different formula, but and sometimes one of these one is more convenient to describe actually the interaction of the AB solution with a less number of the parameter. But eventually, I mean, ideally, we can actually convert this Redlich-Hist type of polynomial to the simple polynomial function. Okay, so for example, here AB solution, so AgCu liquid solution is expressed by this form, and this is more or less same as the Redlich-Hist type of the polynomial. The very first one, XA, XB, and then you have this term here. This term here is same as the LAB, okay, power I equal to 0, and then this term here is the second term with a power 1. So L1, 1 LAB basically is this term, okay? So now let's try to learn how to create this kind of the binary solution by using the random mixing model, okay? So then we can go to this program here. If you click the solution, now we can have this kind of the blank solution actually module here, okay? So now let's try to generate new solution database, okay? So go to the file, and then I'll create a new solution database. So this is the private solution database. And if you already have the private solution database, of course you can open actually that solution actually the database. But otherwise you have to create a new one. So say new, and then you have to say what's the name of your solution. Okay, so I'll try to use this one, in-whole solution. Okay, so this is what I want to use. So you can just say that, okay, if I don't have this one, then remove it. Then I'll just use the INHO, and then it automatically put the SOL, so and then SOLN, and then say okay. Then it will create in-whole solution database. And because I originally already have the actual previous database, it looks like this. But let's try again. So new, and then I'll just go there, some part, detail, so star, sorry. Okay, so let's try to create a new solution database. So you can go to the here, file, and then new, and you have to put the you have to put actually the four character for the name of the solution. So I'll try to make in-whole solution database, INHO, and then if you click, then it will say, okay, you must enter the SOLN. So the fact sage already changed my name as inho soln.sln. So SLN is the solution solution database, extension for the solution database. Say okay. So now you have the new database info. And then there's the function and the solution. So this function here is the gives energy function for the end member of your solution system. So for example, if I have AG and the CU liquid solution, then I have to enter the pure AG liquid gives energy and then pure CU liquid gives energy as a starting point. That should go into this function here, okay? And then I can start to make my solution model inside of this solution data. I can use the solution, I can create the solution by assigning solution model, okay? So let's try. So I want to have the AG and the CU. So then how can I actually create the function? So if you click the function, you can do the mouse right click. You can add your own function by yourself. So for example, I add a function, then it will ask you, okay, name of your function. So let's say this is the A liquid. Okay, AA, for example, and then sharp, and then you have to say assign actually your function name liquid. So for example, like this, okay, then say okay. Then symbol A cannot be used, I'm sorry. Then let's go back again. Add a function, for example, G star liquid. G cannot be used. So we have to go to the function and then say add function star, for example, liquid 1. Okay, then this is the liquid 1 gives energy. So you have to enter your H, S, and then CP function. Then you can actually assign the gives energy. Okay, so for example, we can say that 100 joule. I don't know this one, but whatever number. And S is, for example, 20 joule per mole Kelvin. CP, and as you can actually move here, it shows that okay, you have the function. CP function could be like A plus B star T plus CT C over the T square plus and etc. So you can use this kind of formula. So let's assume I have 30 plus 1 E minus 3 over T, okay, plus for example 0.01 T star T square, for example, whatever function you like, okay? So this is okay. And if you have the actually other thermodynamic property like thermal expansivity and the contractility, you can add it. But this is the minimum actually data we need, okay? And then you can actually have this kind of things there. And then you can also go and save. Then this function will be saved, and then you can use this one later for the you can use it later for your solution actually the database. Okay, so then how can I actually add the pure AG and the pure CU function here? So let's go to the here. So in the fact set, you can generate your own function one by yourself, or you can go to here, compound. So you click compound, and then you have your AG, for example, let's say AG. So I say AG, and then you go to the, for example, FT Lite database, and then I have AG. So I have AG, for example, FCC page. So I can use the FCC page, for example, AG solid later or AG liquid. So I can take a liquid one, so AG liquid, and then press the mouse left key and then drag it and then put it to the function. Then you have AG liquid is copied to the your database, your solution database, for to be used for the future for your solution. Okay, and then also you can take AG solid FCC, for example, and then you can do the same thing, or you can put it to the AG here. Then it will copy the AG FCC AG liquid. So as you can see here, AG, you can see this is HS and then CP function for the FCC, and this is for the liquid phase. Okay, they are copied actually to your solution. And then now let's check CU. Okay, so I have CU here, and then I'll take the same thing, liquid. I cannot put it here. I have to put it now on top of this function. Then you're going to create actually the CU kind of the category, and then liquid CU is copied into this CU actually the database. Okay. And then I have the FCC again, same thing here. So I have FCC, CU, and then FCC liquid is copied. CU liquid is copied inside of this function. Okay. And say yes. Again, save it. Okay. And in this way, you can actually copy the all any end member Gibbs energy from the your compound database and then to the function here in the your solution database. Okay. And also you can create your own Gibbs energy function if it's necessary. Okay. So let's now close this one. So now we have to go to create the solution. Okay, so how to create the solution? So click the solution here and do the mouse right click. Then we have add function or add solution. So now I'm going to add a solution. So solution. Then you have to say the name of your solution. So for example, this is CU, AgCu binary solution. Or if you want to do it for the future, let's say this is the liquid solution, metallic liquid solution. So MLIQ, for example, M metallic liquid solution. And state, I want to have liquid. Okay. And then what kind of model would you like to use for this solution? So this is, so if you click here, it shows that this is model number 1, 7, 12, and etc. Okay. So here I'll first use the model number 1, once lattice polynomial model, assuming random mixing of the species in the once lattice. So Cu and the Ag in the liquid solution. So that's what I want to do. Okay. And then say okay. Then I have liquid C, I have the Cu and A. So I have now blank actually the liquid solution. There's nothing inside. And so if you click, there's no sublattice, no, everything is 0. Okay. There's nothing inside now. So now I'm going to start to create CuAg binary liquid solution. So how can I do that? So then the very first one is sublattice. So you go to click sublattice, and here I have to now assign what kind of species I want to mix in this binary solution. So for example, if you go there, mouse right click, sorry, here, if you go there, mouse right click, so A, on top of this A, mouse right click, then you can add a species. So how many species you need, 1 or 2? So I need 2, okay? So then you have A and then A1, A0 and A1. Unfortunately, in this solution model, because of the programming language, we always start from 0 and 1 and 2 and 3. So when you have 2 species, A0, A1, okay? So A0, what will be your species here? Okay, so I want to mix, for example, Cu or Ag. Let's start with Ag, okay? So Ag is the name of this species, and then formula, what's the chemical formula of your species? Ag, okay? So I want to mix the Ag and the Cu in the sublattice here. So Ag, and then you go here, do the same thing, mouse right click, species, and then I'm sorry, go here, and you have to give the name now, Cu and Cu, okay? So when you do it, I mean, you're probably already interested about what's this chemical group. CHEM group means chemical group. So you can make 2, 3, 4, and then 1. So this is actually important when you go to the ternary system or higher, more than ternary system, because this, depending on the chemical group, we can actually assign the interpolation technique. Okay, but you can overwrite actually that interpolation technique later. But if you, for example, have the same group of I mean, if you Ag and Cu and then some other X species in the same chemical group, then in the fact age, by default, we are using so-called Kohler type of interpolation technique. Okay, and then if AB is the group number 1, and then C is group number 2, for example, then we are using by default tube type of the interpolation technique, assuming the asymmetry of the C component in the ABC ternary system. So for that kind of the interpolation method in the ternary system, we have to properly assign this kind of chemical group. But at the moment, let's forget about it. Okay, so both of them we assign Ag and Cu. Both of them have the chemical group number 1. Okay, now, so when you have the Ag, now we can enter actually and and the member. So for the AG, if you do the mouse right click, then you can now have the so-called add and the member of the AG. Okay, so if you click this one, then you have the AG. Okay, so AG is the species number. I mean stoichiometry is number one. I'll explain this one later again. And then Z, this is the kind of the coordination number is the one. And we don't have to worry about this Z at the moment. And then also stoichiometry. Okay, just leave it as a one and one. Okay. And so name, you can change it whatever name. So for example, you can even say that silver, okay? But the formula is important because this is the chemical formula. And so we have to use the, the periodic, actually the table. We have to use the elemental name from the periodic tables, periodic table, okay? And now here, we have to now say that, okay, this AG, so this AG here, so AG mixing here, we have to assign the Gibbs energy function for this AG. So where's the Gibbs energy for AG liquid? So this one, AG2 liquid. So we have to say that, okay, so as you can see here, A star, so A star formula sharp function name plus B star formula sharp function name plus etc. So A means, okay, constant. So for example, I have 1 times of the formula is the AG, and then sharp function name. Function name is basically this, the liquid is the function name. So in this case, if I want to assign 1 mole of Gibbs energy for this AG, 1 mole, then I have to say 1 star and then AG sharp liquid. Okay, so we don't need this 0 or something, but this liquid is okay. And because this is 1 mole, so even you say one time of the AG formula, or we can just simply say that AG, this is same. Okay, so now AG, we assign the name, something like called the name as AG, and then we give it actually what's the actually Gibbs energy which assigned for this AG. So that's the end member of the AG. Okay, and their Gibbs energy is liquid AG. Okay, and then we have to do the similar thing. So if you click now kappa and then to the mouse right click, and then you can have now add and the member CU, then you can do it. And then you have to now add, okay, kappa, and we leave like this, CU, and formula should be CU, definitely. And then Gibbs energy function, now as we did before, CU sharp liquid, CU sharp. So for example, if you are doing this, then this one is not assigned any of this one, so it cannot recognize it. Okay, so you have to really give the exact name of this one, otherwise FactSage cannot understand what's the actually Gibbs energy of the CU. Okay, so it's good. Now, if you're doing this one, I say that, I mean, let's look at this stoichiometry. What's the meaning of stoichiometry? Okay, so this stoichiometry is the something actually called how many actually the number of the moles of species is connecting with the number of the moles of the your AG formula here. Okay, how many moles of species is mixing in the given solution. So for example, in this case, AG, 1 mole of AG and 1 mole of CU can mix it as 1 mole of the AG CU solution. AG and CU actually replacing each other. Okay, so 1 mole of AG give the 1 mole of stoichiometric species. Okay, for the mixing. But let's assume, for example, this is Al2O3 and then this is Cr2O3. Okay, then Al2O3 and Cr2O3. And if you think about oxygen, so it's same oxygen, so forget about oxygen. Aluminum and chromium can mix together in the given solution. But when you bring the 1 mole of aluminum, Al2O3, there's a 2 moles of the aluminum element is in the 1 mole of Al2O3. Okay, and similarly, Cr2O3, there's the 2 moles of the chromium element actually can coming with 1 mole of coming into the actual solution by addition of the 1 mole of the Cr2O3. Okay, so when you make a solution, Al2O3, Cr2O3, 1 mole of Al2O3, so 1 mole of mixture of the Al2O3 and Cl2O3, even though we assume there's the 1 mole of the M2O3 solution, but in reality, inside of this solution, the chromium and aluminum, 2 moles of the chromium and aluminum is mixing together in the 1 mole of M2O3 solution. Okay, then from the entropic point of view, the entropy actually is the species which is mixing inside of solution. We have two elements like aluminum and the chromium species is mixing inside of M2O3. So for 1 mole of M2O3, we have 2 moles of aluminum chromium X mixing. So in order to actually give this kind of entropic effect correctly, we have to assign, okay, what's the stoichiometry of the species which is coming here would be 2 in this case. So Cr2O3 and Al2O3. So 2 moles of aluminum and 2 moles of chromium actually mixing by mixing over the M2O3. Then this stoichiometry can be the 2. Okay, so it's really the entropic mixing actually species in the given solution. Okay, given actually the end member you are assigning here. Okay. Okay, so this is good. So we have two actual species ready now, and then their Gibbs energy, each Gibbs energy is already assigned for each species. Okay, so basically what we have done is, so far is like this. So in this solution, I say this A Gibbs energy and the B Gibbs energy. And then because this is so the ideal mixing, so this term is automatically determined by this formula. Okay. Now it's ready to actually enter G excess Gibbs energy. Okay. So then how can I actually add excess Gibbs energy? So interaction. So this is actually the section I can add excess Gibbs energy. So how can I do it? So you can go here, AG, and then mouse the the click the actually shift key. No, click the actual control key. Sorry. So AG, click AG, and then push the control key, and then CU. Then both AG and CU is clicked by this yellow color, okay? And then do the mouse right click. Then FactSage automatically know that, okay, you select more than 2 species. So now FactSage want to actually add, okay, some interaction parameter, okay? So the interaction parameter here, add Bragg-Williams type of interaction parameter. So this is G-access parameter, okay? So you see there's the ternary interpolation, Bragg-Williams access parameter, and the add quasi-chemical access parameter, pair fraction access parameter. These three is activated depending on your solution model. So the very first one, Bragg-Williams access Gibbs energy, GE is access Gibbs energy, okay, and this is the random mixing models. This kind of random mixing model, or model number 1, random mixing model, we call it also Bragg-Williams random mixing model. So that's why we say that Bragg-Williams type of the excess Gibbs energy, and that excess Gibbs energy we can use different kinds of the polynomial function, simple polynomial, regular solution, or the Redel-Kist type of polynomial, or Legendre type of polynomial. Okay, so in this case we're going to use the simple polynomial function. Okay, so yes, then it starts to add one simple polynomial solution. And if you like more than one, you go again. Both actually this the AG and CU is still actually the shown as the yellow, and then you do the mouse right click again on top of there, and then you add one more simple polynomial. Then you can have two simple polynomial which is still empty. Okay. Now you can start to enter actually your the excess Gibbs energy. So if all this excess Gibbs energy is 0, this is basically the ideal solution. So ideal solution, okay, between the AG and CU, because there's no excess Gibbs energy parameter. And then the mixing is the ideal mixing, because this model is already assuming the ideal mixing. Okay, model number 1 assuming ideal mixing between the species. Okay, so now if you want to enter the now regular solution type of the parameter, then this, so if you look at this one, QAB, YA, YB, and Y is equivalent site fraction, and this equivalent site fraction is actually noted here. Instead of mole fraction of AB, And this is exactly same actually concept. So equivalent site fraction means at the given site. So for example, this A was the actual sublattice. We have one sublattice, and so given actual sublattice, what's the actual mole fraction of Ag and Cu? So that's we call it as a site fraction of Ag and Cu in the given A site. Okay. So if you have the, for example, B site, then we can also assign uh, the mole fraction of the species inside of B site, and that we call it as the, this kind of equivalent site fraction. Okay, in the P site. Okay, so equivalent site fraction is same as the mole fraction even in the given actually the lattice site. We can assume in that way. So this is same as mole fraction. So XA, XB or YA, YB. Okay, power 1, 1, and then, for example, 1000. Then it means the omega, so regular solution parameter is 1000 for this AB binary solution, this AGCU binary solution. Okay, and the unit is, of course, in this case is Joule. So when you actually create the first actually the when you open the actually your database for the first time, you better check the actually your unit all the time, and in this case it's the Joule. Okay, by default. Okay, so 1, 1 and 1000. Okay, and if you, for example, let's say make it as 0, then this is not actually the affecting your binary system. So when j equal to 0, so when j equal to 0, so this means yb equal to 1. So this is term is eliminated, and so this 1 is affecting only ya, so xa. Okay, then this is not anymore binary term. So by adding this one, you can change your Gibbs energy even for the A component. And in this case, A component is Ag. Ag Gibbs energy can be corrected by this amount. That's what it means. So you should be very careful when you actually assign the power of the AB for for the simple polynomial type of the excess Gibbs energy. So at least for the simple polynomial solution, polynomial actual function for the excess Gibbs energy, you have to add at least more than 1 and 1 power for the A and the B simultaneously. Okay, so 1, 1. And then if you think your actually solution is the subregular solution, you can add 1, 2, for example, with something, or 2, 1 with something, and any kind of complex solution, 1, 3, 1, 4, 1, 5, whatever you like, okay? And then assigning some value. Even the value QAB can be A plus BT plus CTLNTN, etc. So you can enter more than actually the more than one, you can add any complex actually template dependence term for the QAB. Okay, so that's how we actually create the very simple regular solution or ideal solution actually by using model number 1. So once it is there ready, then you can go save and save solution. Then we can use this one now in the Gibbs energy calculation, in equilibrium calculation, or even in the failure calculation. Okay, so I made actually liquid liquid, metal liquid. Okay, now let's try to create a solid solution. Okay, so here as we see we have the copper FCC and the AG FCC solution. Okay, and we can create even FCC solid solution as well. So how we do? So go to the solution again. We have to enter the new one. So go to solution, enter new solution. Now you have to say which solution you want to make. I want to make FCC solution. So and FCC. And then what's the state? And then solid now. Okay. You want to use the still one sublattice, one lattice polynomial function, random mixing model? Yes. Okay. Okay. Then I have FCC. Can you see it? And then you can even actually add some kind of the solution description. So if I click this one, let's try to add this one. So this is FCC solution between A, G, and CU. Okay. And then say okay. Then you can actually see this information later when you click when you actually open the equilibrium program. Okay. Okay. And then now I want to enter AG and CU FCC. Then you have to go click and then click sublattice and go here sublattice, and now go to the right click, and then species. I need two species, and one is AG FCC, so AG again, and this will be CU and CU. Okay, this species name, you can use whatever name you like to. Okay, and then now AG, and then to the mouse right click, and then add in the member. So this is AG formula, and then Gibbs energy is, if you go up here, so that's why I actually copied it here. So this is AGFCC underscore A1. So this is what I'm actually doing. So here, so if you go back, let's look at the, the exact actually the name again. So this is AG sharp FCC under A1. Okay, so you have to enter exact actual name. Okay, and then now kappa, go again, must right click, add the kappa, and then this one was the CU. So if you go here, CU FCCA1, CU sharp FCCA1. Okay, if you don't give the if you don't provide exact name, correct name of the actual the Gibbs energy function, then factor is just simply neglected, and then it will have the some error in the future. Okay, so you have to look at the name very carefully, and then assign the proper actually the function name here. Okay, and then now I want to add the interaction parameter. Then you have to go to the species, because this species is mixing in the given sublattice. So you have to the AG, and then control key, and then CU, and to the mouse right click, and then go to now Bragg-Williams again, simple polynomial. Or if you like, you can do the Radcliffe type. Okay, but I want to actually still use simple polynomial function. And then here, now you can say power 1, 1, so for example, minus 1000 plus 2t, for example, whatever you like. Okay, so good. So we have the one parameter here, and then now let's go to save the solution. So now I have all this solution is ready. Okay, I have liquid solution, AGCU, binary liquid solution, and FCC AGCU solution is also ready. Okay, so now we can use this one in the equilibrium program or phase diagram program. Okay, so how we can do that then? I mean, I can add here directly. So if you save it, after you save it, if you click this one, add inner solution to the database pool, then this one automatically connect your actually the equilibrium program database. And so when you open the equilibrium, you can see that this database is already available. Okay, so let's click that. Okay, then it says that, okay, this one connecting your equilibrium program. Okay, say yes. Okay, now unfortunately it's not connected with the standard version, which I have in the package here. So if you go to the equilibrium program, now let's look at it, how does it look like. And then I say no, yes, I want to now call that actually database. So then you go to the data search, and then you go here, and then you see that in-whole solution. So if you click this one, there's the in-whole, and then we have compound database, because we create this compound database last time by using compound module, and as you can see in the information here. And then we can see also in-whole solution database just created. Okay, so you can click this one, and then you can remove the old list, for example. So I have in-whole solution. Okay, and then if you click OK, then you can use this one for the AGCU calculation. For example, I say here AG and CU. Okay, and the unit, I want to use the unit as Kelvin and the mole, for example, Kelvin and mole, and joule in energy term. Okay, AG and CU, 1 mole, and if you go next, then you can see here your liquid solution and your FCC solution. Okay, So do you remember when we actually have the FCC solution, I say I add this kind of the description for this FCC solution. So that actually information is seen in here. Okay. And then this name MLIQ and FCC, this is same as the name I created in my solution database. Yeah. So here MLIQ and then FCC. So this is the name which is shown in this actually the database page, database and the page name. So that's the page name, and this is the name of your solution. Here the first 4 character here is the first actually the one first word in your solution actually description is taken as a name of your solution. So here first actually the word is FCC. That's actually taken. Okay. So you can use these two, for example, to do any thermodynamic calculation at given temperature. So at 1000, for example, if I click, then I can see that at 1000 I have 2 moles of FCC of the AgCU, and then this is like silver, and this one AgCU and the liquid state, yeah, no, solid FCC state, sorry, and then their enthalpy and Gibbs energy, etc. is given in this way, okay. And now what we can do is also, because this Ag and Cu is not in our compound database, so we can enter the pure Ag and pure Cu into our compound database, for example. And so let's go back now, go to the clip here, and go to compound. And then I'll just add Ag from the FT-Lite database, Ag, and then I'm dragging this one and then put this one into my inno database, base. So now I have pure Ag in the inno base, okay? And similarly, I'll go to the Cu, and then Cu is also available in FT-Lite because we use the FT-Lite database, FCC and the liquid from FT-Lite to create actually our solution. So we had better use the same and the member Gibbs energy. So I'm taking this one again to the Cu. So I have now Ag and Cu in my inno database as well. Okay, and then I can now close this one. I can close this one. And then now if you go back, you are actually data search. Okay, so I go to data search and then refresh. Then this database is updated now, and then say okay, and then go next. Then you can see the actual pure solid and the pure liquid as well. Okay, so I can use all of this one now in the calculation. So if you click it, now we can still see actually 2 moles of the FCC is stable one, and then we can start to see actually some other compound information as well. Okay, and then for example, let's go here as we did last time. So let's take initial condition and take Ag FCC, okay, and Cu FCC from my database at 1000 Kelvin. That's good, 1000, 1000, and 0.5 moles and 0.5 moles. And I want to do the calculation. So next, and then I'm considering only, I'm neglecting everything. I'm considering only FCC solution here and do the calculation at 1000 degrees. So 1000 degree Ag and 1000 degree kappa, 0.5, 0.5 moles, and it become 1 mole of FCC, and their delta H is this value here, okay? This value is coming from my interaction energy here, okay? For example, if this is liquid, it should be exactly this value. Let's try that we get this value, okay? So for example, if I say this is liquid and this is liquid, I don't care about temperature, but let's say just 1000, and then go next. And then if I take only liquid solution, 1000, and then do the calculation, then my delta H for the liquid solution is 2500 joule. Okay, so if you go back again for this one, 1000 times 0.5 and 0.5 at the 0.5 mole fraction. So that is 1000 times 0.5, 0.5, it's about 250. That's 250 joules. Okay, that's exactly the same as this delta H. Okay, Is it okay? And this delta S is, of course, in this case, is ideal entropy term under this condition. Okay, that's how we create actually our solution database by using the solution program and then connecting that into the equilibrium program too. Okay, so that's enough. So then we can actually start to create a more complex solution. Okay, let's try that in the next session. Okay, thank you very much.